start? Because wouldn't that be a shame if I forgot to record? Good morning. So we're going to start. We finished talking about kind of some properties of the normal distribution, and now we're going to go through and actually do an example that shows all the different questions that we could ask and tackle. So if we imagine a cereal manufacturer, then they're filling the boxes, the cereal boxes. But I think we all understand that when we go to the store and we grab a box of cereal, even if it says 16 ounces, this is an American question, obviously, but it doesn't matter. Even if it says 16 ounces, we understand that it's not going to be exactly 16 ounces, right? It could be a little bit less, it could be a little bit more. But if it's a lot less, then we get upset, right? We say, I'm not paying for that. And you put it back and then some other person pays for it. But still, so if the boxes are labeled 16 ounces, then of course the company wants to have at least that much cereal in each box. So the problem becomes that if the machine, right, so this machine sprays out, 16 ounces with every spray. So if you set it to 16, well, the machine is going to distribute the cereal according to a normal distribution, right? It'll average 16, right? But then some will be really low and some will be really high, right? Some will be overfilled. So if you set it at 16, what do we know about the mean? Well, then we know that half of those boxes, roughly, would be underfilled, under 16, and the other half would be over 16, right? So that's not really what we want, right? Because then consumers would be unhappy, exposing the company to bad publicity and possible lawsuits. It sounds terrible, right? So to prevent underweight boxes, the manufacturer has set the mean to be a little bit higher, right? Because then what happens is your normal distribution, if it was centered on 16, if you bump it a little bit higher, then, more than half would fill to 16, right? So there's a typo in here. I catch it every time I use these notes, and then I never fix it. I think I've used this example for a few years now. It's embarrassing. Based on their experience with the machine, this isn't even the worst typo there is out there. I know they're out there, but just never fix them. The company believes the amount of cereal that the boxes fit a normal distribution. So now we're given that it follows a normal distribution with a standard deviation of 0.2 ounces, and the manufacturer decides to set the machine to put an average of 16.3 ounces in each box. Okay, I did keep the little footnote here that since no packaging process is perfect, there will be minor variations. And that's what we're here for, right? Statistics is studying that variation and how can we kind of control that, or not control it, but how can we avoid underfilling boxes, for example. Okay. So let's read through all these parts and kind of get a handle on what we need to do. So what proportion of the boxes will be underweight? Remember, a proportion is a probability, which is roughly a percentage. So the question could have had any one of those words here, right? And the goal is still to find the area under the normal curve. So what proportion of the boxes will be underweight? Okay. We often have these kind of tricky questions where we need to understand what it means to be underweight. And in this case, an underweight box is anything less than 16 ounces, right? So that can be tricky, right? So less than 16 ounces. I have no idea what ounces are, or I have no grasp of 16 ounces, but I do know what a cereal box is, so that's a good step. Good first step, I guess. So then we're going to figure out what proportion of boxes weigh more than 17.21 ounces. Okay, so just another weight that we want to find a probability associated with. Then what proportion of boxes will weigh between 16.11 and 16.61 ounces? I'm terrible with pounds too, but yeah. 454 grams, that I can get behind. I know it's so funny because usually if someone asks me how tall I am, I'm 5'7". But that's just because growing up, that's just what you say. But I don't actually know like how long a foot is. It's so bad. I've got a pretty good idea now, but still no clue. Imperial, because I grew up in Sweden, right? So we're completely metric. There's no talk of inches or anything. They're insane. But here we are, ounces. So what if they want to publish a guarantee that says no more than 4% of boxes weigh less than some amount, right? What value should that be? So we have, I don't know, it's more in the States, I think, where, you know, pizza companies have a guarantee, oh yeah, we'll get to your house within 20 minutes. How do they decide that 20 minutes is a reasonable time to do it, right? That's because the times it takes to deliver is follows a normal distribution. And then they would base it off of that, right? So they've made a calculated risk. And some delivery times will take longer, right? But they feel pretty confident that they're able to get it under that 20-minute mark, right? So same thing here. If they want to say that no more than 4% of the boxes are going to weigh less than some amount, we can figure out what that is, right? Notice that now we have the area under the curve and we want to work backwards. So that's what we ended talking on. And here we'll see an example. And then we're going to figure out how heavy are the top 25% of the heaviest boxes, right? If we're way overfilling that top 25%, then we need to reconsider what we're doing, right? And so nothing to it but to do it, I guess. Here we go. See what's going on. And remember, I had the R code on the side, so you can play around with that and see what the P norm command and the Q norm command. But for here, I'm just going to use the Z tables. Okay, so part A, what proportion of boxes will be underweight? So the first thing I want you to do, even if it doesn't make sense right now, is to draw the curve. So draw the normal curve. And it's so funny. Everyone's always the same. I don't need to draw it. I understand the question. Okay, great. Still draw it though, because there's going to come a time where you need to be able to wrap your head around the question, and drawing it is going to be the easiest way. So if we start out drawing them, then that's going to be a good thing. And there's been so many times where students come to me afterwards and they're like, I thought it was so stupid that we were drawing these curves. I didn't get it. I didn't see the point. But then they do, and it makes sense. Okay, so we were told that the boxes, so the amount of cereal follows a normal distribution. Who doesn't like drawing? Exactly. It follows a normal distribution with a standard deviation of 0.2. And we set the mean to be 16.3. Okay, so the center here is going to be at 16.3. And then I'm just going to write sigma equals 0.2 down here somewhere. I'm not going to do little ticks or anything because we don't need to do that anymore. Okay. So the point that I'm interested in is what proportion, so what area under the curve will be underweight, so less than 16 ounces. So remember here, this axis here is just a number line, right? So of course, 16 would go somewhere down here. What I want you to remember is that you don't need to spend a lot of time figuring out where 16 goes. It's just to help you visualize the areas. So often I'll just kind of put points at the halfway mark, even though they should be way out in the tail, or maybe they should be really close to the mean, but often I'll just kind of put a mark here. And it's just to visualize. Okay. So what I want to find is I want to find this area. Okay. So what we're going to do, right, is, okay, so we know how to find areas under the curve. We need the Z table, but in order to use the Z table, we need to find the Z score, right? So I'll kind of go through that thought process here for the first one, right? To find the area under the curve, we need the Z table, but to use the Z table, we need a Z. Okay. So remember, Z is X minus mu over sigma. And we established that just yesterday. X is always going to be the value that I'm interested in, right? And so here, X in this case is going to be 16. Yeah. So Z is 16 minus 16.3 divided by 0.2. And I don't have my, I'll bust out my calculator here. 16 minus 16.3, and I'm just going to get right to it, divided by 0.2, puts me at a Z of negative 1.50, right? I'm going to tack on that second decimal place because Z should be to 2 decimal places to match the table, right? You don't need the 0, but 2 decimal places to match the Z table. Okay, so now remember the Z table gives you the area to the left, right? So it's always going to give you the area to the left. In this case, right, because this is kind of our starting case, that is the area that we want. So once we find Z equals negative 1.50 in the Z table, then we have the area to the left. So let's see here. Go to the tables and I'll grab it, grab a portion of it at least. I'll have it big and then I'm going to scrunch it up because we don't need it that big in the notes, but I do want to show you where it's coming from, especially these first couple of times. So negative 1.5 is this row here. But then because my second decimal place is 0, that's when I go for this, this column here. One mistake that I see quite often is that everyone or people just use the 0, 0 column. You don't make use of the second decimal place. So in this case, yeah, we're using 0 because that is our second decimal place, right? But you want to be taking advantage of the second decimal place. So at the intersection, we find 0.0668. Okay. So as promised, I'm going to shrink this up here. Well, maybe not. Okay. Let's see if I can. Whee. Okay. Using the Z table, we find the area to the left. And so here's where it gets a little bit tricky is usually if I'm asking you to show your work, then I want you to explain how you got that value of 0.0668. And so how you would do that is with this standard blurb that we're going to establish here. I'm also going to show you probability notation that I think you're going to gravitate towards, okay? Because writing out this blurb, it's pretty tedious. So using the Z table, we find the area to the left of Z equal to negative 1.50 is 0.0668, right? So instead of writing this, or we could write the probability that Z is less than or equal to negative 1.50 is 0.0668. Something I will take marks off for is if you try to tell me that negative 1.5 equals 0.0668. And I see that a lot and I understand what you mean, but that's not true, right? So you want to be really careful. Okay? Do not write something like Z equal to negative 1.50 equals 0.0668. That's not true. Okay, so you want to really put the stops on and say, okay, is what I'm saying true, right? In this case, I understand what you're doing, right? I understand that you went to the Z table and you saw negative 1.5 and then you found the area, but that's not what you want to be saying. What you're actually saying is that the probability, right, the area under the curve, that Z is less than or equal to negative 1.5 is 0.0668, right? So you can use this probability notation. That's way faster, right? But if that doesn't make sense to you, or if you don't like that, then your other option is writing out this blurb, right? Just explaining what you did. Using the Z table, we find the area to the left of Z equals whatever is blank. Okay. So you've got options depending on how comfortable you are with this probability notation. And I think as we get lazier and lazier, probability notation starts to look more attractive as we go, right? Okay, so it's catching up. What proportion of the boxes will be underweight? 0.0668, right? Or 6.68%, if you want to talk about that, of the boxes will be underweight. Usually I'm not expecting a final blurb, and I know that's kind of bad, but usually once you have the number, that's fine, you can move on. But for this one, I'll do a little blurb. We have found the proportion of boxes that are underweight is 0.0668. If it asks for a percentage, I would convert it to a percentage, but that's also the probability of having an underweight box. What proportion of boxes weigh more? What proportion of boxes weigh more than 17.21 ounces? So this one I am going to move a little bit quicker because time is at my heels. I know it doesn't feel like it, but we've got a lot of work to do. And I do want to focus on D and E because they're going to be the most foreign. Okay, but let's do B. So first things first, we're going to draw out the curve And again, it's going to be a normal distribution because it said so. And it's centered on 16.3 and sigma is 0.2. And the value that we're interested in was 17.21. Okay. So that's going to be your X, because that's the point that you're interested in. And we want to know what proportion of boxes weigh more than 17.21. Okay. So again, I'm not going to explain why we have to find a Z-score. It's because we need to use the Z table. I'm just going to go ahead and do the calculation. In general, what you'll find is that you'll start out with some X, and then you'll turn that into a Z using Z equals X minus mu over sigma. And then that Z is going to be turned into some proportion or probability using the Z table, right? So there's kind of like a pendulum here, right? And so you have an observation, you convert it to a Z using that Z calculation, and then you can use the Z table to find the probability or the proportion. Later, what we're going to find is we could go the other way as well, right? If we have some probability or proportion, I could map it back to a Z score, and then I could use that Z score to solve for X, right? So I like to have this little kind of Z's like I like to think of Z as like a gateway drug, right? You have to go through Z, right? So it's always going to be a two-step process. So for us here, we need to first convert it to a Z score. So Z equals X minus mu over sigma. So Z is 17.21 minus 16.3 over 0.2. Grab my fancy calculator. It's actually not fancy. I shouldn't call it that. Z is 4.55. What does a Z score of 4.55 mean? Well, it means that 17.21 is 4.55 standard deviations above the mean, right? So we can always interpret the Z score as a number of standard deviations above the mean or below the mean if it's negative. Okay, so then now, instead of using my usual blurb, because I think you guys can handle it. Okay, fine. You can handle it, but I can't. I'm still going to write my blurb, but then I'm going to show you with the probability notation. I was just going to throw you guys to the wolves and go probability notation already. We'll get there. But what I'm going to say is using the Z table, because I realized I'd send you down a dark path here. But we know what to do, right? If the Z score is off the table, which it will be. So using the Z table, right? We find, well, if we go there, I'm not going to bring it in this time, but we are going to be on the positive side of the Z table here. And so if I go and I try to go to 4.55, I max out at 3.49, right? And so 3.49 has an area to the left of 0.9998, which we looked at last day. So that's okay. So I just want to show you how to handle this. So using the Z table, we find the largest Z score is Z equal to 3.49, which has an area to the left of 0.9998. Okay. So what we want is actually the area to the right, right? Looks like someone used R. So for these written questions, I love that, but we're gonna try to figure out how do we do it with just the table. So, and I'm on board with that. So, so here we want the area to the right. So if we have the area to the left, then we can find the area to the right. So which has an area to the left of 0.998. So the area to the right of Z equal to 3.49, because that's the one that I'm talking about here, is 0.0002, right? Or maybe I'll show is 1 minus 0.9998, which is 0.0002. This means that Z equal to 4.55 must have an area to the right less than 0.0002. This means Z equal to 4.55 must have an area to the right smaller than 0.0002, right? If we have a look at our standard normal curve, we're being told that Z equal to 3.49 has an area to the right of 0.0002. So now if I head out here and Z equal to 4.55, we could say it's approximately 0 or just less than 0.0002, right? So what we could say is we could use, or the probability that Z is greater than or equal to 4.55 is 1 minus the probability of Z being less than or equal to 4.55, which is 1 minus approximately 1, which is approximately 0, right? I'm being, if we get greater, so even if you find a Z score that's way out here in the tail, then you can just say it's less than 0.002 or approximately 0. Is that what you mean? Nice. Okay. Good. So that's good, right? Because a box weighing 17.21, that's really bad if it's supposed to be weighing 16. But what we found is that the probability of that happening, or the proportion of boxes that where that happens, is approximately 0. So that's good. I guess I should say, therefore, the proportion of boxes that weigh more than 17.21 ounces is approximately 0. That's good. Notice that R code on the side, right here. Oh, sorry, it's catching up. We did the calculation here and it was 2.68 times 10 to the negative 6. That's really, really small. That's approximately 0, right? And so we were able to get kind of more precise values here if we use R, but using the Z table, we max out at 3.49 on either side. Okay, so C, what proportion of boxes weigh between 16.11 ounces and 16.61 ounces? Because I won't remember those values, I'm just going to steal them here and bring them down. Hey, come on. Okay, so again, what are we going to do? We're going to draw out our curve, draw our normal distribution here. It's still centered on 16.3 and sigma is still 0.2. And so now I actually have two values that I'm interested in. So I want 16.11, which I can see is going to be below the mean somewhere. So 16.11. And then 16.61 is going to be above the mean. So somewhere around here. Remember, you're just using the graph to help you map things out, to help you figure out what you need to solve for. So the area that we want is this area. There are lots of ways that we can find that area. My preferred way is if I take the area to the left of this upper bound, and then I take the area to the left of this lower bound. What if I just lob off that the area to the left of the upper bound, right? So you can treat them as puzzle pieces, and there, like I said, there are lots of ways that we could go about finding this, right? But yeah, orange minus purple, that's math for you. Yeah, take the orange puzzle piece minus the pink puzzle piece and then you're good. Right, but however your brain works to try to figure out, but as long as all you're left with is this central area, then you're good. What's going to happen then is that we're going to have a Z score for the lower bound and a Z score for the upper bound. Right, and so what I'm going to do is I'm going to use X lower, and then I'll keep using these colors, X upper. There's like a really creepy banging going on in my house. I'm alone while you guys are all here. Please stay on the line. Okay, so it's like right across the wall here. Okay, so what I'm going to do is I'm going to have to find a Z score for either of these or for both of these, and then use those to find areas. So yeah. I'd prefer a raccoon over a zombie, I guess. Yeah. So let's see here. So my Z for my upper, and notice how I'm just using little subscripts. That's just for me to keep track of which one. You could use 1 and 2, but I like upper lower. Is going to be my X upper minus mu over sigma, which is going to be 16.61 minus 16.3 divided by 0.2. So 16.61 minus 16.3 divided by 0.2 gives me a nice 2 decimal Z. Usually we'd have to round, but as long as you're rounding properly, you're going to be good. Maybe what I'll do is I'll put these side by side. So then my Z lower is going to be my X lower minus mu over sigma, which is going to be 16.11 minus 16.3 over 0.2. which is 16.11 minus 16.3 divided by 0.2. Again, a nice rounded value to 2 decimal places. I don't have to do any work. It's great. Okay. So what I want is really the area to the left of 1.55, right? That's going to be this whole area. And then I want to lob off the area to the left of the pink side. So what I'm going to do is I'm going to use probability notation here. And I'll start with the orange one. So the probability that Z is less than or equal to 1.55 is what? Well, make sure you're on the positive side because I mix them up. I guess I put my upper on the lower, anyways, whatever. 1.55. I'm getting 0.9394. Now my eyes do jump around here, but I'm feeling pretty good. 0.9394. So then I'm just going to write 0.9394. If you wanted to write it out as a blurb, you'd have to say, using the Z table, we find the area to the left of Z equal to 1.55 is 0.9394. That's a lot. No, thank you. Here, the probability that Z is less than or equal to negative 0.95 is, so I have to be on the negative side, negative 0.95 is whoops, sorry, it's catching up, but I did do it, I promise. Negative 0.95 is 0.1711. So that's going to be 0.1711. So to keep it on the same page here, what I'm going to do is now I'm going to combine the two, right? So then the probability that Z is between negative 0.9, oh, I didn't give myself enough room here. The probability that negative 0.95 is less than or equal to Z is less than or equal to 1.55, because that's what we want, right? We want the area in between here is 0.9394 minus 0.1711, which is 0.9394 minus 0.1711, 0.7683. So 76.83% of boxes are going to be between 16.11 ounces and 16.61 ounces. Okay. Tried to keep it on the same page here. All right. You can do fancy things like you could start off with an X in here and then you could manipulate all the sides, right? But I want to finish this example today. So maybe I'll parking lot that for the review, but you could try it out. Okay. D, that's the guarantee. Okay. So they want to publish a guarantee that says no more than 4% of boxes weigh less than some amount. Okay. And so what that's going to look like in terms of our curve is still centered on 16.3 and sigma is still 0.2. So now what we want is we want to find some cutoff here that we don't know what it is, where we force this area to be 0.0400. Notice that I'm matching the table because the table entries always have 4 decimal places. So 4% is 0.04 and then 00. Okay. Remember, you're always going from an X to a Z to an area, or from an area to a Z to an X. So now what we're going to do is you're going to scan the table for the area closest to 0.4 or 0.04. Okay, being really careful that you have the proper number of zeros. So using the Z table, we find the area, or the table entry, I should say, the table entry, just to match the little help note that they have on there. We find the table entry closest to 0.0400 is, sometimes we are able to find the exact value, but sometimes you just have to find the closest one. So 0.04 is going to be on the negative side, right? I know that much. And you might be tempted to go for something like 0.0004, but that's not what we want, right? We get into the 0.04s kind of here. I transition from 0.0392 to 0.04. Let me see if I can highlight that. So it looks like I'm choosing between these two values here. These are going to be the closest to 0.04. Notice that you can read these from right to left, but moving down the rows. So there is order, but it's not the order. It's not in the order that we think, because the decimal places are increasing as we move across. So it looks like 0.0401 is the closest thing that I have to 0.04. So I'm going to jot that down, but also I'm going to map that back to a z-score, negative 1.75. is 0.0401, which corresponds to Z equal to negative 1.75. And maybe I'll go grab a little snippet of that. Come on. Like that. So then in Z equals X minus mu over sigma, now I have Z. Z must be negative 1.75, which is X minus 16.3 over 0.2. Oops, did a sigma, but it should be 0.2. Solving for X, right? And I think on that formula sheet that I posted, there is the formula that's already solved for X, but I actually prefer fewer formulas and then just figuring out what I need to solve for, right? But that's a matter of preference. So I need to multiply both sides by 0.2. So negative 1.75 times 0.2. And then I need to add 16 oops, hey, where's my pointer? Add 16.3 to both sides. So plus 16.3. I get an X of 15.95, which means that our guarantee, no more than 4% of boxes weigh less than 15.95 ounces. That's a pretty good guarantee. Oops. What was it? No more than 4%. No more than 4% of boxes weigh less than 15.95 ounces. So the last question, I think we want to know, how much do the heaviest 25% of boxes weigh? Pretty sure it is. I'm going to steal it here though. Let it catch up. Oh. it's another case where we need to work backwards. How heavy are the top 25% of the heaviest boxes? And because we're talking about weights, right? So here's our distribution again, sigma is 0.2. So now at some point that we're trying to solve for, this area is going to be 0.2500. Okay. Now, that's on the right side. There are a couple of ways you can get sneaky with as you get more comfortable. You could say, okay, well, the Z score that I want is actually going to be the positive version of the Z score on the lower end with an area of 0.25, right? You could do that. Or what I prefer to do usually when I start is, well, if I have 25% in the upper end, I must have 75% in the lower end. So then what I'm going to say is, using the Z table, we find the table entry closest to 1 minus 0.2500. And maybe I'll bump this over here. Wink. Which is 0.7500 is, so now I'm going to try to find 0.75, because remember the table entries are only giving you areas to the left, which is, I know it's going to be on the upper end. Why is that? Because it's more than 50, right? Or 0.5. So now I know I'm going to be on the positive side here, and 0.75 looks like here's where I transition between 0.7486 and 0.7517, right? And so, and I think those are my two options. So I need to figure out which one's closest. It's going to take a little bit of calculator work. How I think of this one is that it's 17 away from 0.75. I know that's kind of weird, but then I do 0.75 minus 0.7486 and find that it's 14 away. It's weird, right? But whichever way you find which one is closest, it's going to be this little guy here, whee, which corresponds to a Z of 0.67. I'm going to bring this in here. Down to the wire, I know, is 0.7486, which corresponds to Z equal to 0.67. So then Z equals, and maybe I'll do it on the next page here. Z equals X minus mu over sigma. So 0.67 is X minus 16.3 divided by 0.2. 0.67 times 0.2 plus 16.3. X is 16.434. So the heaviest 25% of boxes weigh more than 16.434 ounces. Nice. I know I'm out of time. I do want you to just read that last little bit on how to evaluate if a distribution is normal, just so you kind of have seen it. But otherwise, nice work. And if you have any questions, let me know. Otherwise, have a great Thanksgiving weekend.